Now I want to talk to you about how this idea of symmetry, circling back to the idea of unification in mathematics. I said earlier, continents of mathematics, number theory, harmonic analysis, geometry. A Langland's program that unites them. Langland's program in which one of the main ideas, main concepts, which permeates Langland's program is the concept of symmetry. But so far, I have only shown you how symmetry plays out in geometry, because we talked about transformations of this bottle or a glass or things like that. We have also talked a little bit about how symmetry groups are useful in quantum physics. But now I want to show you how the same groups, symmetry groups, also show up in the study of numbers. So what kind of numbers I'm talking about? Well, first whole numbers, of course, so 1, 2, 3, 4, 5, etc. Then you got 0, and you got negative numbers. So this is what we call whole numbers or integers. So you have this infinitely many integers. These are the first numbers we encounter. Then we want to divide things. So that brings us to the idea of rational numbers, which of course, by the way, not called rational because they are well behaved, but that's because they are ratios, fractions. They're ratios of two integers, like 7/31 or 9/25, etc. Okay? And for a long time, mathematicians actually thought that those were the only numbers that existed. Pythagoras only thought only fractions existed, or had the right to exist. And whenever a number appeared which was not a fraction, it was not a legitimate number somehow. That needs to be sort of swept under the rug, skirted and condemned. Such as square root of 2. Very quickly you encounter square root of 2. What is the square root of 2? You can look at the square of side 1 and the diagonal on that square. The length of that diagonal will be square root of 2 by Pythagoras' theorem. So the number seems to exist. It's the distance between those 2 points, between those 2 corners in a square, right? But then very quickly you realize, it's very simple proof, to see that it cannot possibly be written as a ratio of 2 integers. Okay? So we have to, if we want to do justice to numbers, we have to throw in this number. We have to include it. Okay? So if we include, what does it mean we include it? Well, we include this number, then it kind of like opens kind of almost like a Pandora's box. You have to then allow also to multiply this number by a fraction, because we already accepted fractions. And you should also allow to add a fraction to it. So you get numbers like this, a plus b square of 2. And this is already good because, first of all, if you have 2 such expressions, you can add them up, just component-wise, right? But also you can multiply the 2, because when you multiply, you will get, again, numbers of the same form, but also you will get, square root of 2 multiplied by square root of 2. But when you multiply square root of 2 by itself, you get 2, just by the very definition of square root of 2. That the square root of 2 is 2, right? So you never leave. If you take these numbers, you can add them up and multiply them, and you never leave this realm. It's closed under addition and multiplication. So we get a new numerical system. And mathematicians call it a number field. We get this number field. And now here comes the main point. The main point that once you start studying this, you notice that such a numerical system has hidden symmetries. In this case, the symmetry is flipping the sign in front of square root of 2. It changes the number, obviously. I mean, if b is not, unless b is 0, then it doesn't change. But if b is non-zero, it changes the number. Say you had 1 plus square root of 2, it will go to 1 minus square root of 2, so you get a different number. In what sense is it a symmetry? It is a symmetry in the sense that when you do that, all the, it will preserve all the properties of those numbers. For example, if you take the product of 2 numbers before you apply this operation, or after you apply this operation, or you can apply the operation to the 2 numbers and then take the product, or you can take the product and apply the operation. It will be the same. And the reason why it is so is because square root of 2 and minus square root of 2 solve the same equation, because each of them is a square. Each of them squared gives us 2, right? So you see, it's a very important point, because if you take minus something and you square it, the minus is gone. So here, this is an important point. You have an equation, x squared equals 2. And it has 2 solutions. One is the square root of 2, and the other one is negative square root of 2. So there are 2 solutions, which as it should be, because the equation has degree 2. So there have to be 2 solutions. Square root of 2, negative square root of 2. And there is a symmetry which exchanges them. And that's what we see when we consider these numerical systems. And this is a very powerful idea, which is one of the most important, I would say, one of the most important ideas of all of mathematics, which actually came to us through the work of a brilliant French mathematician, Frenkel Galois. He was a genius who actually died in a duel at the age of 20. And actually, he died on May 31st, 1832. And today is May 31st, so it's kind of, it's a day of, not exactly around, number of years, but it happened on this day in 1832. And, the night before he was killed in a duel, he was frantically trying to finish, he knew that he was going to die, I guess, subconsciously, and he was trying to finish his papers, which, by the way, they were so revolutionary that mathematicians couldn't understand them for another 20, 30 years before, he was given his due recognition. And I always think of, I kind of always conjure up, when you study mathematics, mathematics is like a love affair to us mathematicians. And when I think about it, I always, it always brings this image of Galois, this young guy. He's writing this. What is he writing? He's not writing a love letter to his girlfriend. He's writing a love letter to all of us in some sense. He's writing this stuff because he wants to share it with us before he dies, right? And I really think that Galois groups are like the wonders of this world, really, like, Egyptian pyramids or the Hanging Gardens of Babylon. The difference is we don't have to travel through time and space to find them, to see them, to appreciate them. They're right here at our fingertips. They belong to all of us. Nobody can take away Galois groups from us, right? I mean, we may not be aware that they are out there, but they are out there and they're waiting for us to discover them. So how does it work? Galois was interested in trying to solve polynomial equations. What do I mean by polynomial equation? Well, at school we studied this equation, quadratic, which we call quadratic equation, ax squared plus bx plus c equals 0. There is a formula for it, which I'm not going to write, so as not to trigger any unpleasant memories. Important thing to know about that formula is that it involves taking square root. Square root is involved somehow, right? Well, of course, for example, even for the simplest one, x squared equals 2, we have to take the square root of 2, right? But if you want to write a general formula in terms of the coefficients, you see, the coefficients are fixed, a, b, c, and x is the variable. We want to solve it for x. And we use a, b, and c as input. So you ask, what is the formula for x given a, b, c? It's a formula which involves a, b, and c, and it involves the square root. Once we understand that, and by the way, this was already in a book published in year 830 by Al-Khwarizmi, which had, in the title of the book, there was the word algebra, which gave the name to the subject, algebra, year 830. Then, of course, mathematicians were wondering, well, can we also solve a cubic equation? So they will start with x cubed. And yes, there was such a formula produced in the 16th century. And then for the quartic equation, equation of degree 4, also in terms of taking roots. But for cubic, you need cubic root. And for degree 4, you need root of order 4. What we call radicals. Radical is either square root or cubic root or nth root. And then the question was, can we do it for the 5th? Can we do it for the 6th? And so on. And so for almost 300 years, mathematicians tried to find a formula for an equation of degree 5, just like that, in terms of its coefficients, in terms of radicals. And they couldn't. And then Galois came, and he said there is a reason why you cannot find it. It's because there is no such formula. So you see, there is a fundamental difference between equations of degree 2, 3, and 4, and the equation of degree 5 and higher. And the way he explained it is by using what we now call Galois groups, by using groups. He said, let's not try to solve it. Let's not try to find a formula for the solution. Instead, let's look at the symmetries. It's almost like, the French say, cherchez la femme, And Galois said, cherchez le groupe, search for the group. Search for the symmetries. That's where you will find it. That's where you will find the answer. We can look at the symmetries, and we can discern the structure of solutions by even not knowing what the solutions are. if we can understand their symmetries. Here's how it works. The simplest way Galois group works is going back to our square root of 2. Remember, there are two solutions of the equation x squared equals 2. Square root of 2, negative square root of 2. We can exchange them. It is like exchanging the two wings of a butterfly. A butterfly is symmetrical. Why? Because we can exchange the two wings, it will stay the same. Likewise, we can exchange the two roots of the equation x squared equals 2, it will stay the same. So this butterfly group of two elements, exchanging or not exchanging the two elements, is the Galois group of the equation x squared equals 2. It has very simple structure. And here's what it will look like for an equation of degree 5. A general equation of degree 5 will have 5 different solutions. We don't know what they are. We would like to write a formula, but we don't know what they are. It's okay. Let's just represent them by these little circles. A symmetry then of the equation would be a permutation of these 5 solutions. The way one of the permutations is written here, but there will be many others. The first one will go to one of the 5. The second one will go to one of the remaining 4. The third one will go to one of the remaining 3, and so on. That will be a permutation. If you have 2 such permutations, you can apply them back to back. You'll get a new permutation. That's why it will be a group, for the same reason that rotations of a bottle form a group. And now the point is that this group that for a general equation, the symmetries of the solutions will comprise all possible permutations. There will be 120 of them, 5 factorial. 1 times 2, because first time you choose 5, then you choose 4, then you choose 3, then you choose 2, then you choose 1. There's no choice. So 5 times 4 times 3 times 2, if I calculate it correctly, is 120. Which, by the way, this group, interestingly enough, is almost the group of all symmetries of icosahedron. The 5th element that Robert was talking about, Platonic solids. And the most complicated Platonic solid is icosahedron, which has these triangles. There are 5 edges emanating from each vertex. Its group of symmetries is almost the same as this group, is up to a factor of 2. So it's very interesting that the same group actually shows up in geometry as well. But Galois' point was that this Galois group of symmetries of the quintic meaning equation of degree 5, has a much more complicated structure. Not just because it has 120 elements, but just because we can look at its structure. It has a much more complicated structure than the groups that show up for polynomials or for equations degree 2, 3, and 4. And its structure is such that it prevents us from finding a solution in terms of radicals. So I don't want to get too technical, but it's basically the idea is that you can only find a formula in terms of radicals if the group has a certain simple structure. And from degree 5 and higher, it just doesn't. That's why there is no formula. That was his solution. So what I want to say is, Galois did not solve the problem the way it was understood. The way it was understood is, let's just find a formula. We found it for quadratic and cubic and quartic. Why can't we find it for quintic? But he kind of hacked the problem. He looked at it in a different way. He said, let's look at symmetries. And this way, he found out why the original problem was not, posed in the right way.